A couple of weeks ago, the Shenzhou 13 mission returned to Earth, bringing back a crew of 3 astronauts, Zhai Zhigang, Wang Yaping, and Ye Guangfu, after 6 months spent on board the Chinese space station. In this episode, let's focus on the Shenzhou Spacecraft, the crewed vehicle that has been sending Chinese astronauts to space for the past 2 decades, and more specifically, let's talk about how it returns to Earth. I'm Jean Deville, welcome to the Dongfang Hour, a channel where we talk about Chinese space.
Ladies and gentlemen, welcome to the Dongfang Hour. Please make sure your seatbelt is securely fastened.
女士们、先生们，我的飞机已经离开上海，我们预计在当地时间下午6点25分左右到达。
The Chinese space station, also known as the CSS, orbits the Earth at an altitude of 400 kilometers, meaning that it travels at a staggering speed of 28,000 kilometers per hour. And bringing astronauts on the CSS safely back to Earth means that you have to bring all of this velocity down to 0 while maintaining the integrity of the spacecraft and while keeping also the accelerations experienced by the spacecraft under a reasonable threshold to avoid naturally killing the astronauts. And just like Crew Dragon, Soyuz, and Apollo and other crewed spacecraft, this is an absolute challenge for Shenzhou. In the latest iteration of the Shenzhou spacecraft, the entire process takes roughly 9 hours, from the undocking process with the Chinese space station all the way to the point when the return capsule performs a soft landing on Earth. Let's detail these steps one by one, but first let's start with some background on Shenzhou. Shenzhou is China's first operational crewed spacecraft, and its design dates back to the 1990s. It bears a strong resemblance with the Soyuz spacecraft, and similarly it is composed of 3 modules. You have the orbital module, which serves as an additional pressurized quarters for the astronauts when the Shenzhou is in orbit, and this module has an androgynous docking mechanism based on Russian standards, and which is used to dock to the Chinese space station. Next, there's the service module, which provides the electrical power thanks to a pair of solar arrays with a total span of 17 meters. It also houses attitude and orbital control systems, with notably the 2.5 kilonewton thrust main propulsion engines and the 150 newton attitude control engines at the base, and some other lower thrust reaction control engines on the external wall. It also holds thermal and environmental control systems for the spacecraft in orbit. And finally, you have the Reentry capsule, where the astronauts are seated, and which is the only module that is returned to Earth in a controlled way. The Shenzhou spacecraft is launched on board a Long March 2F rocket, and up to 2 Shenzhou spacecraft can be docked to the Chinese space station at a time using the front and radial docking ports. When returning to Earth, the standard landing area is now the Dongfeng landing site in Inner Mongolia, in the middle of the desert and in proximity with the Jiuquan Satellite Launch Center. And the advantage of this is that Jiuquan can provide support with its already existing tracking and search and rescue facilities and equipment. So let's now take the example of Shenzhou 13, which was docked to the radial docking port. At the start, at roughly T-9 hours before landing, the Shenzhou spacecraft undocks with the Chinese space station using a mechanical pusher system to avoid having to fire engines when in proximity with the space station. This process is rather slow, we're talking about a couple of centimeters per second, and the Shenzhou spacecraft stops at 2 intermediate parking points at 19 meters and 200 meters. And following this, the Shenzhou uses its attitude control engines to flip 90 degrees to face forward in its trajectory and makes various orbital adjustments to ensure that it's in the correct orbital plane. At this point, the hatch between the orbital and the reentry modules has been closed, and the command is given to release into space the air that's contained inside the orbital module. And this is done because this will be useful at a later stage when both of these modules separate. The Shenzhou spacecraft then remains in orbit during 5 orbits until it reaches the orbital position where it can perform the deorbit burn and the separation. In practice, this lasts 7.5 hours, which can seem quite long, but it's actually a significant improvement over previous versions of Shenzhou. In Shenzhou 12, for example, the previous Shenzhou mission had to perform 18 orbits over a period of 28 hours until it reached the point where it could perform a deorbit burn. And coming next, we have the separation and the deorbit burn, which takes place over 3 steps. The first one is to get rid of the orbital module, which has no further purpose. To do this, the Shenzhou spacecraft turns 90 degrees with the help of its attitude control thrusters and discards the orbital module. The reason behind this specific attitude is to avoid performing separation in the direction of the trajectory to avoid any risk of collision. Once the separation has been performed, the Shenzhou spacecraft now turns another 90 degrees with the propulsion module facing forward and the return capsule facing backwards. The 2.5 kilonewton main engines are then fired during approximately 2.5 minutes, significantly cutting down the spacecraft's speed. And the way orbital mechanics works is that when you lose velocity, this has a direct impact on your altitude, and this effectively puts Shenzhou into a re-entry trajectory with the Earth. And this phase is also critical because the precision and the length of the firing are key in determining the landing area, and it's also interesting to note that the deceleration burn is done with a non-zero angle of attack. Once the deceleration is complete, the Shenzhou spacecraft has lost more than half of its initial altitude of 400 kilometers, and at this point the Beijing Aerospace Flight Control Center communicates a first estimation of the landing area to the rescue teams on the ground. As the Shenzhou spacecraft then continues to lose altitude, when it roughly reaches 145 kilometers, it performs another attitude control maneuver to have the propulsion module pointing upwards, forming a 145-degree angle with the trajectory, and following which the propulsion module separates. The return capsule then adjusts its attitude once again to have its heat shield point in the direction of the descent trajectory. Then the Beijing Aerospace Flight Control Center announces a second estimate of the landing area, and this marks the beginning of the next phase, the atmospheric re-entry. It is during the atmospheric re-entry that the Shenzhou spacecraft loses most of its velocity. When it starts entering the atmosphere, it is at massively hypersonic speeds with Mach numbers that can easily reach beyond 20, and this triggers the formation of a massive shock wave, which creates a huge temperature increase downstream of the shock, up to several thousands of degrees. Shenzhou, in a similar way to Soyuz and Apollo, uses a blunt heat shield. The blunt shape has the advantage of detaching the shockwave and pushing it forward away from the spacecraft, decreasing, therefore, the thermal constraints. The heat shield also uses ablative technology, meaning that parts of the shield absorb the heat by slowly melting and evaporating, and this outward flow of ablative material also thickens the boundary layer, significantly decreasing the heat flux. Ablative technology has played a really important role in the atmospheric re-entry over the past roughly 60 years of space exploration. And interestingly, the astronauts can actually observe this process of burning material coming off during the descent by just looking through the re-entry capsule window. Naturally, this whole fiery process has the tendency to increase the cabin temperature. And while there is a lot of thermal insulation to keep the astronauts at a reasonable room temperature, the Chinese also do another operation that they call yuleng, meaning that they make the temperature inside the cabin drop before the re-entry phase to anticipate the increase further down the road. Now, during the re-entry, as the atmosphere grows thicker and thicker, aerodynamic drag naturally becomes the major force slowing down Shenzhou. But to avoid following a purely ballistic trajectory, Shenzhou has a non-zero angle of attack, meaning that it generates lift, which enables the return capsule to have a much smoother, more controlled descent, during which the astronauts experience at most an acceleration of 3 to 3.5 Gs. And this is a pretty standard amount. I believe that's what people experience in roller coasters, although during a much shorter amount of time. The way this angle of attack is created is by having an off-axis center of mass, which will in turn trigger an aerodynamic moment, aligning the center of pressure, of mass, and the velocity vector, effectively creating an angle of attack. During re-entry between the altitudes of 80 kilometers and 40 kilometers, the Shenzhou spacecraft can also experience something called the Blackout Zone, where it can no longer communicate with the Chinese ground stations or the Tianlian relay satellites, and this is due to the formation of a layer of ionized air from the heating that's happening upstream of the heat shield and which interferes with radio communications. This blackout can last up to 4 to 5 minutes on Shenzhou. And finally, Shenzhou reaches the lower layers of the atmosphere at roughly 10 kilometers, which is an altitude where commercial jets also fly. At this stage, the spacecraft's velocity has been reduced to subsonic speeds, but it is no longer slowing down because drag being proportional to the velocity squared, drag naturally plays a smaller and smaller role in slowing down the spacecraft, which at this stage has stabilized at the speed of 200 meters per second roughly. So to continue the deceleration, at this point, this is when the Shenzhou spacecraft deploys the parachutes. A small auxiliary pilot parachute is first released to pull out and deploy the drogue parachute. The drogue parachute then slows down the Shenzhou spacecraft for roughly 19 seconds, bringing it down to 80 meters per second, and then it is jettisoned, pulling out the massive 1,200 square meters main parachute in the process. The main chute then opens progressively over 8 seconds to avoid too massive a shock for the astronauts, and this brings the speed of the capsule down to roughly 7 to 8 meters per second, or roughly 25 to 30 kilometers per hour. At this point, the capsule and the astronauts start preparing for the final landing, and the Beijing Aerospace Flight Control Center announces a third estimate for the landing zone. At 6 kilometers of altitude, the reentry capsule discards its heat shield, exposing 6 solid-fueled landing retro rockets used to cushion the impact. Remaining hydrazine propellant inside the Shenzhou capsule for reaction control is also purged because it is no longer useful, but more importantly because it is highly toxic and could endanger the rescue teams on the ground. To absorb the landing impact, the astronauts raise their seats on a dampening mechanism, which acts like a buffer to absorb the kinetic energy during the final impact. It's worth noting that the astronauts' seats are inclined, forming an angle of 20 degrees with the spacecraft floor, and the reason for that is that G-force accelerations perpendicular to your spine are much less harmful than parallel ones. Also, each seat padding is custom made and molded to match the astronaut's body shape, similar to Soyuz, and the idea is to absorb energy as efficiently as possible. So at the speed of 8 meters per second, roughly 30 kilometers per hour, the Shenzhou capsule is still moving at dangerous speeds for an impact. And so a fraction of a second before hitting the ground, the Shenzhou spacecraft fires its retro rockets, bringing down the impact speed to 2 meters per second, or in other words, less than 10 kilometers per hour. And shortly before this, the Beijing Aerospace Control Center would have announced the fourth and final coordinates of the landing area as various rescue helicopters and vehicles rush to that location. And so that's how the Shenzhou spacecraft returns to Earth after undocking from the Chinese space station. There's a lot of cool physics and science behind the deorbiting and the reentry mechanisms that we mentioned earlier, and you can definitely go further with an interactive learning platform like Brilliant.org, who are kindly sponsoring today's video. Brilliant is a fantastic tool where you can learn any science and engineering related subject on your own in an interactive way, which gives you more hands-on experience than just watching lecture videos. Related to space exploration, you have, for example, more basic courses on what is mass and what is, the fundamentals of Newtonian physics. And as you get more advanced, you can touch on topics like elliptical orbits or Hohmann transfer orbits, which are essential to understand how satellites and other spacecraft evolve in space. Each concept is explained in an intuitive way, making the learning curve much less daunting and covering the basics all the way to the most advanced topics. You can use the link in the description below to start this learning process for free, and thanks to the partnership with Brilliant, the first 200 listeners will also get 20% off the annual premium subscription, unlocking all the problem-solving courses and challenges. A big thanks to Brilliant for their support and to you for watching this video. And as always, a special thank you to all our Patreon supporters, with a special note to Jeffrey Schweitzer. You guys really make this channel more sustainable on the long term. With that being said, I'll see you in the next episode.